Lab 1's objective is to observe and model motion of constant velocity. In doing so, we observe differences between the two descriptions of the same motion and what could cause those differences. The two descriptions include observing the motion of an object and modeling that observed motion computationally. For the observational portion, I rolled a paint tube across a level surface. Here is it playing. Here in this video, you can see that I clipped off the start of the paint tube from rest. Since start from rest would have varying velocity, clipping the start ensures only constant velocity motion is observed in the clip. I have marked 30 different positions of the object in equal time intervals. These intervals are a third of a second. By using Tracker, I was able to get the position and time values of the object, and it is stored right here. We're only looking at the x values and not the y values. You can also see that the graph is shown right here, and we'll be going into comparative analysis later in this video. The motion of the paint tube, I use GlowScript. Here in the code, I use a Lab 1 starter code as a template. The changes I made to model the motion are as follows. I first set the initial velocity, which I found using the position update formula, which is r final equals r initial plus velocity times delta t, and that value is right here. I got these values from the observed motion through Tracker. Here, delta t is about a third smaller than we see in the observed motion, but it shouldn't make a difference in the computational modeling as it's constant velocity motion. Then, in this loop, I let it run for as long as my observed motion ran, that is the length of the clip. In the loop, I made sure to update the position with the same position update formula here. Velocity does not change, and the force on the object should be 0 because it's constant velocity in accordance with Newton's first. When we run this program, you can see the motion of the object as well as the position time graph, and you can see how it's constant velocity motion because the velocity has not changed with time. And here are the printed values of the position in the x direction and the time it was captured at. Here in the spreadsheet, I copied the values from Tracker for the observed motion right here, and from GlowScript for the model motion, which is down here. So I took these two values and I graphed them in a line chart to see the difference in the motion. As you can see, there's a slight change in the experimental and model motion. The velocity slows down in the observed motion. This is because in the real world, there's forces of friction and air resistance acting against the motion of this object, which makes it eventually stop. To get closer to the model motion, I could use smoother surfaces and smoother objects to reduce the effect of friction. To answer the lab's questions, the motion is currently in the positive x-axis. If the axes were switched so the motion was in the negative x direction, this would make the position time graph have a negative slope, which would make the velocity negative as well. The magnitude of the vector variables, like position and velocity, will however stay the same. There would be no semantic difference in the comparison, and either axis could be picked. So I can show this change in the axes through GlowScript. So I have changed the velocity to a negative velocity. The magnitude is the same. However, since the position would be negative if the axes flipped, the velocity would be negative as well. So the rest of the code stays exactly the same. So I'm going to run this program. And you can see that the motion is now in the negative x direction. And the position versus time is also in the negative direction. You can see this has a negative slope. Velocity, however, remains constant, just like it did before. So there is no semantic difference in the experiment or the lab, but it is in the negative direction. Now for the next question, as I mentioned before, there is a force of friction acting against the motion of the object, which is primarily causing this difference between the experimental observation and the modeled position of the object's motion. And although smaller magnitude, we also see the force of air resistance acting against the object. So in order to mimic the modeled motion of constant velocity, there should be an external force in the opposite direction of these forces and equal in magnitude, so the net force is 0. If the net force is 0, the object will continue to move with constant velocity in accordance with Newton's first law and will mimic the modeled motion. This concludes the comparative analysis between experimental observations of an object under constant velocity and its computational model of the same motion.